thank you very much for the invitation. I'm very thrilled to tell you a bit about what I'm doing or what I have been doing. So there's a reason why it's not one consistent title like you would expect. I have to agree that I'm leaving before. This is because it's going to be kind of three short topics, three ideas that I'm thinking about. And one of them is kind of a more finished project, which is lattice gauge theories. And throughout the talk, we'll be using tensor networks for all of them, or at least trying to use them. And the first one is kind of more done and dusted, like that's a paper. The other two are more ideas, more things that I would like to discuss here. So this is an invitation of me giving you some input, some ideas, and then actually having a discussion if you fancy to do so, to think about where that could lead and where we could go with that. So the idea here is that tensor networks is kind of the one thing that goes through this talk. In the first one, we are going to use it as an ansatz for the ground state, which is actually how tensor networks kind of became a thing in condensed matter. They are a good ground state ansatz for gapped local
Sorry
Hamiltonian.
for a stupid interruption,
Yeah.
but if that is our Zoom link, then the people are seeing neither the screen nor the speaker.
No, screen is shared. They can see the slides.
Oh,
So
okay.
they should be able
Okay,
to.
fine. That's
Okay. So then I'll move my computer to here, and then I'll be more in the picture, I guess.
much better.
Perfect. Thank you. And then in the second and third one, we are kind of going to abuse them a bit. And in the one case, use them as a tool for classical optimization, which they actually became kind of known for in, for example, finite element computations for classical systems. And then we're going to use them lastly in topological data analysis as a numerical tool, again, to find ground state degeneracy, or we're trying to. So since I'm going to talk a lot about tensor networks, I know that you had a talk on tensor networks last week. So make sure to speed me up if you feel like all of this is already known. We are going to start off gently, and then we kind of ramp up a bit later. So if you feel like this is all known because you heard it last week, just tell me. So first of all, why do we care? Like, why do we want an ansatz for a ground state? Why don't we just solve the system exactly? For quantum many-body physics isn't that easy. If you even want to consider kind of an n-body Hamiltonian or n-body system of Ising spins, you have 2 to the n versions how to kind of pick your ground state. You have kind of 2 to the n possibilities. In the classical case, you just have to find one minimal energy configuration. In the quantum case, you would have to even store the exponential overlap of all of them, because possibly they all play a role. That's kind of harsh. Like me as a person coming more from numerics, if you tell me to store something that's exponentially big, I won't be enthusiastic about it. So the idea here is maybe we can find approximations of that ground state that only need polynomially many parameters instead of exponentially parameters that I would need to store the exact ground state possibly. Of course, there are many ways to pick them. You could just go for a mean field ansatz. You could do kind of all kinds of approximations. And now the question is, can we find one that's meaningful? So can we find a tiny bubble in Hilbert space, like a kind of subspace there, where we know that it's useful? So that important ground states are in there. And one of these kind of classes are tensor networks, actually. And for local gapped Hamiltonians, these are actually efficient to represent the ground state. So now, what are tensor networks? I just put them there on the slide. So maybe just let's have a kind of a quick recap of what tensor networks are. And if we just take our most general superposition state here, which is I, now the Ising basis, and then we have our sum over all the coefficients that we have there indexed by our spin labels, we can start thinking about what would be a good approximation. Like, how do we find that small bubbles? And I just put up some coefficients there, and one thing that you could do is maybe I just kill all the small coefficients. It turns out that's not a very good idea. Like, that's not actually how you get a good approximation for a good ground state. You need to do something a bit more structured, because in that way you have no idea what you're kind of throwing away. And the idea of a tensor network is to kind of make that a bit more of a local decision. What do I mean by that? If we imagine, now we are introducing a bit of kind of image notation here, because this is what we're going to use throughout the talk. What I mean is the CI1 to I5, this is this big tensor of coefficients. It has kind of labels there going with either 0 or 1, depending on your spin state. And then it has all the coefficients in there. What I mean by that is that you basically plug in numbers onto those small blue legs, and it will give you back one number. That's just the same idea as if you put 2 indices to a matrix, you will get a number. If you put 5 indices to that tensor here, you'll also get a number. So a matrix in that notation would be just one bubble with 2 legs. Now we just have a big bubble with 5 legs because I chose to represent a 5-spin system. Okay, so far? Like I think you have seen that notation to a degree already, so I'm not telling you anything new right here. Now, how do you go from there, which has exponentially many parameters, something that has polynomially many parameters? Well, the idea here is to cut up that tensor. And how you do that is you kind of reformat that tensor and put all the kind of 4 legs to the left, 1 leg to the right. You interpret it as a high-dimensional matrix, and you use an SVD, so a singular value decomposition, which means that you have in the second line 1 blob on the right, the diagonal singular values, and all the other rest on the left, and then I continue cutting. And what you get is kind of the third line there, which is kind of a bunch of tensors with singular values in between them. And for example, this was the way Gifre-Vidal did it in the first papers, actually keeping these singular values explicit. And nowadays, it's kind of more common to absorb them into one of the tensors, which side you don't really care, except for you're doing numerics and you're really interested in canonical forms and efficiency, or you're trying to prove things, then canonical forms are also very useful. For us right now, it doesn't really matter. The funny thing is, I used equal signs here all the way. So this is not an approximation in any way, because approximation with equal signs is a weird thing. So what I did here is I just rewrote the whole tensor, and I didn't tell you how big these smaller matrices are. Because what happened here, we just cut up a big thing into a bunch of smaller things that have now 3 legs, right? Initial thing, 1 big thing, 5 legs, now many smaller things with 3 legs, and I just left out the kind of stub legs to the sides because, well, open boundary conditions, you can imagine a stub leg of dimension 1 there, it won't change it. Now, these objects there now have 3 legs, and just to give you an intuition of what happened in the meantime, or how we could cut here and reduce dimension, you could cut on the black legs. So this is kind of a matrix or a tensor indexed by the eyes, and then you have multiple matrices because you have still 2 legs open. What do I mean by that? Well, singular value decomposition is something you can cut very easily. Me as a physicist, I like to have a visualization of that. So, for example, you could take an original image. This is a national park, Joshua Tree National Park in California. And this has, if you take the diagonal, 1080 singular values. Now you can just reduce it to 20, and you get kind of a very good approximation of that image. And this is the same thing that we're trying to do. We're cutting up the image into an SVD, reducing the number of singular values, and we get kind of an approximation of that image. Now, this is obviously image dependent. You see kind of this rastering there, like this grid pattern that you see. If you take a well-known artist from the Netherlands, Mondrian, you will see that this image is much more amenable to approximation than the other one. You don't see any grid pattern because, as it turns out, Mondrian likes to align things by a 90-degree angle with the canvas. And so the grid pattern that you saw in the other image is actually now perfectly aligned with the image. What I want to take you away from that is matrix product states won't well approximate any state. The idea of approximating that state, if this was a tensor network state, might be much harder than approximating a Mondrian image. So there are certain states that can be well approximated, and now we can kind of put everything together and have our MPS done and dusted. We have a way to truncate the virtual bond dimension, which are the black legs, and I'm trying to keep that throughout my slides. So black legs are always virtual. Virtual means they don't play any physical role. They are just my way of approximating the state. Larger virtual bond dimension means more approximative power, like more states can be represented faithfully. Then the blue legs are actually the physical input. Like if you were to act with an operator on this state, you would put an operator from the top, which would have legs on top and bottom, and then would act on that state, transform it, possibly entangle it more, entangle it less, depends on the operator, and then you have another state. So now we also see why these things are called matrix product states. You have a lot of A's there, and this is basically just a product of matrices. If you just have a look at the indices, the alphas there are all virtual indices. So these are all contracted together, and we are starting with a one-dimensional thing, ending with a one-dimensional thing on that contraction, and it all falls away to one number, depending on the eyes there, which gives you the combination. Yes?
Just make sure I understand.
Yeah.
Like these black lines, like the dimension represent the number of zero value that you use. I mean,
Yes, so the dimension, like these capital D's here, these ones here, would be called the virtual bond dimension. And that is just the number of singular values that I'm keeping in that truncation procedure. In the picture that was 20, usual calculations are rather in the order of, let's say, 500 to thousands if you want to do precision numerics with that. So yeah, please ask questions. Like we're going to see a lot of these images in a second. So this is a good slide to kind of ask about them. But yeah, this is kind of our state. Note that we are not really writing the state here in terms of bubbles and lines. We are writing the coefficient. Like there's always a basis assumed underneath. I know that this is one of the big confusions that people sometimes have. Like you're writing a number here, or you're writing a tensor. As soon as you put a basis at the end, you have a state again. So that basis is agreed to be the computational basis if nothing else is noted. And it will be the same for my slides. Just to make it clear, so this equal sign is a bit of sloppy notation, but it's kind of common in the field. So we're going to adapt that. You don't seem entirely happy?
No, sorry. Truncation, basically, you're talking about the eyes, right?
Yeah, I'm talking about these eyes here.
Yeah, okay.
That they kind of disappear when I'm doing the equal sign. So the sum over the eyes isn't kind of explicitly there anymore. And I would have to write the sum over I, all the i's on top and the state I at the end to make it really like an equal sign, like equivalent to the last line. This is just slang notation that is used about Nintendo networks. So you will mostly never see people actually writing the sum and then the kind of state there because it's always agreed beforehand that it's kind of a useful basis that you're using. And this is kind of usually the computational one.
Has it helped in the past to use other bases than the computational basis?
Usually you kind of just do it implicitly by kind of so it's kind of a convenient basis that is usually chosen. So for example, I'll go and use a fermion number basis because kind of a spin basis doesn't really work for me because we're looking at fermion Nintendo networks in a second. So usually it's the one that's most natural to think about in your problem. I don't know whether people actually have kind of done a lot of work on artificially changing it into something easier, because as soon as you're going to, like, if you're doing analytical proofs, you usually don't care about the basis so much. And if you're doing numerics, you usually kind of start restricting your tensors to kind of a certain subspace. And then it's kind of easy to think about that in a basis that you can easily calculate with on P.
But for example, you could imagine that you use a very complicated basis.
And
And then starting from, but you know what it is, and you somehow understand it, and then from that you get sort of another bubble in your Hilbert space that explores a completely different region.
well, I think changing the basis shouldn't change the entanglement properties of the state that you have there. Like I think the proofs are basis independent. Like for example, the one by Hastings or so, where he states that all local gap Hamiltonians are efficiently representable by tensor networks. I don't think that he explicitly makes use of that. This is a computational basis. But
It could be highly entangled spaces. That would change the entanglement.
Yeah.
It's just
no, it's true. I've never thought about that. So that's certainly interesting to think about it. I would be very surprised if you get a very different bubble. I would imagine that you get kind of a similar bubble because kind of.
but somewhere else in the space.
Yeah, but somehow this is very local, right? Because you can really inject like a local eye at every position. So it would not, like if you have a very high entangled, maybe it doesn't make much sense. Also in the picture.
I'm thinking Kolmogorov complexity where you sort of move to a completely different region and then sort of explore that.
Yes, I agree. Like, what's the comment?
What's the
So,
comment?
typically, one works in the basis where the impressions is the best.
Yeah.
Which often comes from locality of Hamiltonian interactions.
Which then makes it kind of a lowly entangled basis because all the Hamiltonian interactions are local. Yes, it is. Yeah.
Just checking, when you use the word basis, I think you're talking about one of the individual systems, right? One of the capital and individual systems.
Well, yeah, or this kind of big tensor product of all of them there. like spanning that kind of, oh,
Don't be too distracted by these messages.
It's only Ido.
So yes, in that case, a single spin would have just a 0-1 computational basis. Like, you keep it coming, right? Here we go. So yeah, it's like basis in the sense of for one single qubit, it would be 0-1. And then if I want to kind of have the whole Hilbert space of all the systems, just tensor produce them all together. And this is just implicit notation here. The commata are actually tensor products, and I'm just too lazy to write them kind of in its full beauty.
I think on your second slide, you referred to this small bubble as a subspace, but if you bound the virtual bond dimension, I don't think it's subspace. These states form a basis for the whole space.
Yes, I agree. Yeah.
More complicated.
Yeah, it is more complicated than just a subspace. I agree. Like, slip of language. Okay, so we just saw how to go from kind of one big blob of coefficients to kind of smaller tensors, but actually you can't store that big blob, right? So it's exponentially big, so starting from there is kind of a very weird thing to do. And this is also not what we're going to do for the rest of the talk. We're going to do it the other way around. If I could just kind of do the small bubbles and then link them together in a way, I would also get a tensor network state. And this is actually what has been done in condensed metric called the AKLT model. And what you start with is kind of entangled pairs, and you just write them in a kind of a higher dimensional analog of the Bell state. And then you start tensor producing them together, and the AI alpha beta that I'm using here are actually the same that we had on the last slide. So what you're doing is you're taking two of the virtual bond dimensions here, alpha and beta, the two sides, and kind of weight them together to create a bigger spin, which would be the one on the top. So just coming back to our Ising example, you would have kind of high dimensional, capital D dimensional entangled pairs, and then project them together to get you one of the I's, which would be kind of an Ising spin again. So this is just the same procedure as before, just kind of the opposite direction. Instead of saying I take a big tensor and chop it up, now I take small tensors and glue them together. And this is much more amenable to kind of working with if you want to construct a state, because writing down that big kind of exponentially large tensor is most probably not a lot of fun. So this is kind of the way that we are going to structure, because here you come from local constituents, and thinking of lattice gauge theories, you want local symmetries in the end. And so this is why we'll be working in that approach. Okay, so that was my, let's say, 15-minute introduction to tensor networks. Now we are going to kind of dive into what's actually happening. And this is going to be tensor networks and lattice gauge theory. So these are all the people involved here. That's Ariel, Umberto, Sergey, Snir, Ignacio, and Ares, like working on different instances. Like this is a couple of papers that I'm going to summarize now into one big blob. And our idea was, how do you construct good ansatz states for lattice gauge theories? And the first thing that I already heard before the talk is, what the hell is lattice gauge theory? Why do we care? Very good question. This is why you care, or why at least I care, or you could care. If you do quantum electrodynamics as a physicist, you're very lucky. Your interaction is actually rather weak, and what you get is kind of this very famous term 1/137 there. And the Feynman diagram above is just for illustration, because that's a typical process in QED. We don't care about that too much here now. The idea is just, if I wanted to develop in that kind of weighting of the interaction vertex alpha there, that's a very nice perturbation series to do. Like if you have 1/137, then 1/137 squared, that falls off rather nicely. So you hope by going to a finite amount or a finite depth in your series expansion to get really good results. Well, maybe nature isn't always so nice. And it turns out that the interactions of quarks, so the constituents of protons, for example, are not that nice. When they interact, you actually get kind of an energy-dependent coupling. And that means the lower the energy becomes, like we have just this Q in giga electron volts here. The idea here is just right side is high, left side is low. You're starting at 0.1 or so. So there you can do a perturbative expansion. It's below 1. You can hope that your perturbation series will converge. If you're getting up to 1 or 0. And a couple of 9s up there, your hope might be a bit slimmer. So the problem here is you really can't do perturbation expansion on the non-perturbative QCD like the quark confinement thing up there. But this is exactly the region where the theory becomes really interesting. So now you're sitting there and you're just like, well, I can't do it anymore, so what do I do? Well, what people in the late 70s like Wilson thought is like, well, if the thing in the continuum is very difficult, maybe we can nail the theory down on a lattice. So what they did is they took their system, took the Lagrangian, discretized the whole thing, then wrote down the action for that, which is just a time integral over the Lagrangian, and then made a statistical physics system out of that. What do I mean by that? If you usually have your kind of action, you will have an e to the I action in there. This is much shorter than I would usually do this. I apologize for that, but there's kind of two topics coming after this, so we're kind of going a bit quicker than I would usually go. The idea is if you rotate now time, which is a totally artificial thing, which you take time is now minus imaginary and something that looks a bit like the temperature, and you get something that is exponentially damped, which is much nicer for simulation because it doesn't widely oscillate. Now the idea is if I take that and Monte Carlo sample with that, all my problems are solved. Except for the sign problem. And that might be one of the big words that you have been hearing if you have ever been sitting in a Monte Carlo kind of flavored talk. This is one thing that they're always afraid of. Like if your system has a sign problem, Monte Carlo people really don't like the system anymore. And the idea here is this idea of sampling breaks down if you're not sampling with respect to a proper probability distribution. And probability distribution for me now just means that my probabilities that I'm expecting are between 0 and some maximal value, so I can normalize them back to 0 to 1. If your probabilities suddenly become negative, that's going to be a problem for your sampling algorithm because you can't sample a negative amount of time. So this is just what happens here. If you put, for example, you put in fermions or a chemical potential. So there are kind of big gaps in our understanding of QCD just because we can't compute it. And you just rotated away time. So from tau, you went to something that is imaginary time, which makes your system look a lot like a statistical physics system, which is great because you can kind of build on all the work that has been done on statistical physics before in classical statistical physics. On the other hand, you lose any intuition on what time actually means in that system. So you get expectation values for the ground state, for example, but thinking about time evolution is much harder. So these are two of the problems just due to this ansatz. And our idea was, what if we take a step back? And this is also not our idea, like Kogut and Susskind have proposed that already back in the 70s, that you take your system, you describe it instead of a Lagrangian equivalently with a Hamiltonian, and then you just do a variational algorithm on top of that. They weren't so fond of variational algorithms because the computers back then really didn't know what to do with that. Like computing resources weren't big enough to actually store these states or to do anything useful with them. So this is kind of coming back to an old idea, using your 101 in quantum mechanics, using a Hamiltonian and just evolving a state. Wait a second. If I'm talking about Hamiltonians, Hilbert spaces, then we need an ansatz state, right? So let's get an ansatz state. So this is a lattice gauge theory. The blue dots are fermions. The greenish dots are your interactions. Yes.
Just a quick physics question. I suppose that quantum thermodynamics is a relativist theory, no?
Yes. Yeah.
So how do you deal with Hamiltonians in that picture? It's probably not so straightforward, right?
Yes. So there's two ways here. So first of all, as soon as you're on a lattice, you're not relativistic anymore because you kind of have a momentum cutoff.
Sure.
And so you regain the relativistic, like the Lorentz invariance, upon taking the limit. And now, like, limit of lattice spacing going to 0.
I see.
This is not something that we're going to do here. For us, lattice spacing is a constant, and we're just simulating for a given lattice spacing. And there's a whole field that does these continuum limits, they are called. Second thing, if you kind of, this is also true for the action, of course. Now, the art is to find the first art is to find an action that has a proper limit and goes nicely to the continuum theory. That's not easy. And the second thing is to find a representation of that action in terms of a Hamiltonian that does the same thing nicely. So this is what they did in the kind of late 70s or mid 70s. Right. They actually wrote down these Hamiltonians and showed that by doing that limit, they obtain the correct physics in the end again. So we are building on top of that. So the Hamiltonians that I'm going to show in the very end are not my Hamiltonians. They are just taken from very famous papers, and we just simulate them using a different method.
Have you also gone from non-zero temperature on the left to zero temperature on the right?
Like the whole left formulation is kind of you're cooling your system. Like by doing time evolution, you're cooling further and further towards zero.
Well, okay, but at any tau, you have a temperature.
Yes.
Yeah.
But
And on the right, you don't have that tau anymore. So is it zero temperature from the
yes,
start?
yes.
Yeah.
Like we are zero temperature from the start. Here, like the more you kind of evolve your system, the colder it gets. And at some point, you're expecting your thermal kind of fluctuations to be below the energy gap that you're looking at. And then you're basically cooled enough. Basically, you get an additional dimension, which is temperature. The larger you make that dimension, the cooler you get. It's, yeah, I know it's sort of physics intuition. This would be kind of, unfortunately, a whole other talk, how this relates between the two systems. So I'm kind of hoping for a bit of leeway here. So the idea here is, if you're thinking about how we compose systems and you raise it completely correctly, like you have to have a basis, you have to combine Hilbert spaces. So this is what we're doing here. You have a Hilbert space of the gauge field, and you have another Hilbert space for all the fermions, or all the fermions. And I wrote that it's not equal. And that's the whole business of lattice gauge theories. This tiny sign there of being kind of a part of the bigger space and not being exactly equal. That's the whole deal. Because what you have is conservation laws on that lattice. And the intuition behind that, we're going to make it clear in a second, is the Gauss law. So kind of there's a conservation of electric fields and charges, and you have to obey that in your simulation. And what we can write down, for example, is the most general state that you have kind of a big superposition of all the gauge fields. So we are now in the gauge field basis. There's some basis that the gauge fields are diagonal in. I'm choosing that to characterize my states. And then the fermionic part, the psi f on the bottom right corner, that will be dependent on the gauge field part of the Hilbert space. Yes?
Can I quickly clarify? So you're talking about Hilbert space, but there are no free legs sticking out. Like, are they supposed to be?
Ah, sorry. This is not a tensor network yet.
Okay.
This is just a lattice. Like,
oh,
so there will be legs sticking out in 2 slides. This is just a visualization of the lattice that we're allowed to work on.
One of the reasons that this is kind of a subset of the larger Hilbert space, that you almost choose which fermions are interacting with each other. If I look at the lattice.
Yes and no. If you give me 1 slide, then we can figure that out together, because this is what kind of makes your subset, like being a subpart of that. Sorry. Yes. We go.
What is this?
Ah, okay, yeah. So now we are thinking about kind of the gauge that you can have. It can be either a continuous gauge group, think about U1, SU2, SU3, or it could be something discrete like Z2, Zn, which is kind of my favorite pet theories, because they are abelian and they're easy to sample because you only have finitely many elements. Now, if you kind of want to have the most general superposition, you would integrate over all the gauge configuration that you can have on your U1 ring of possible gauge field configurations, and then would kind of put a coefficient in front of all of them, which is kind of now hidden in the psi f. This is a bit like similar to the idea of having this general superposition state, which has all these Ci's to Cn's there. There it was kind of spin up, spin down, so two distinct states. Now it's a continuous gauge group, so the gauge fields become continuous, so we have to integrate over all configurations. If you feel like more comfortable, you can think about the integral as a sum sign, and then the G's will just be up and down for Z2 lattice gauge theory. It will do precisely the same job.
So what is X and K?
X and K here, I should explain that slide better, I figure. X is your position on the lattice, but the blue dots are making up the lattice in my mind, and so I have to specify direction where I'm going. And the direction is K, so it's either horizontal or vertical, and then you kind of address a given gauge field, small g, and by just addressing a certain side in the direction. And then you have your green dot that you're addressing. There's basically just a common slang notation in lattice gauge theories to address a certain side.
So these DG operators, they act on all these edges, basically.
They act on all the green dots on the edges, yes.
Is it kind of the overlap between like the interaction interaction, the fermions?
Right now, we are just kind of making sure that there's kind of a well-defined superposition state. There is no overlaps here whatsoever. I'm just trying to write down in some maybe too fancy way a big superposition state. We are going to calculate something with that state on the next in 2 slides, so maybe that makes it easier to see what I mean by that actually. So now just coming back to that not being equal to the whole Hilbert space, you have, like in classical electrodynamics, you might have seen that that's one of the Maxwell equations if you have no charges. It just tells you that no electric field from nowhere. And that is kind of intuitively a good idea. If you have 2 charges, you have an electric field in between. If you have a varying magnetic field, you should get kind of an electric field as well. But if you have just 2 charges sitting somewhere or no charges sitting nowhere, then you should have no electric field. And this is just what that said, no divergence of the electric field. And this is something that we have to obey as well on our lattice gauge theory. And this is why it's not equal, because as soon as I have certain gauge fields, I will have certain electric energy configurations there, electric fields. But then the fermions have to match that. And if they don't, it's not considered a physical state. So I kind of have very local constraints on my physical state, and I have to encode them. Now, there are 2 ways of doing that in a numerical simulation, of course. You could just penalize all the states that you don't like to a very high point in the spectrum, like putting a big kind of projector there with a big weight, and you're getting rid of them. The problem is that this usually doesn't converge very well, because you have kind of very kind of different dimensions in your Hamiltonian. You have some stuff that is really small that you want to do accurately, and you have other parts that are really big and shooting you out of the spectrum. So what we did is we wanted to write down these states appropriately. And this is what we're going to do now together. We're going to figure out why these states are useful, and then we're going to design them. So the first thing is we're going to take an observable O that is just acting on that gauge field part. So now if I'm taking that state, I'm kind of pulling it apart. You'll have 2 parts, like in the numerator, you'll have something that acts on the gauge. I can pull all my fermionic states through. I just have a norm, and I have a big sum at the bottom from that norm over the whole state down there. Does anybody recognize something about this expression? I can make it a bit easier. This part. It looks a whole lot like a probability. Right? You have a norm, that's something that's positive, or norm squared to be precise. And you have something that's a bit like a partition sum, like the sum over everything, over all the possible norms. Well, if I call that P, it's a probability, and now I can Monte Carlo sample the thing. Okay, just kind of rewinding, I told you that there are problems with Monte Carlo sampling these systems. So kind of there's a clash here. And obviously I just didn't solve the sign problem. We just did something, because there's no free lunch usually. We just chose an ansatz state. Well, later there might be. I was told I didn't come for that, but I very happily take it. Yeah.
Something confusing about the second green line. Is there like a D missing in front of T prime?
Oh yeah, sorry. Typing these slides very quickly because there was lights on set. And that D most probably stayed on the kermes.
So that's really just a normalizing factor.
Yeah. This is just a normalizing factor. It was just me kind of skipping the D there. Down there. Yeah, it's back here. It's back in the game down there. So now, obviously, we didn't solve the sign problem just by kind of introducing an ansatz state. The big point here is this is kind of biased towards these ansatz states. So everything that I cannot express in these ansatz states, I cannot sample. So there's kind of a very big restriction here, meaning that these ansatz states have to be useful. Otherwise, I just sampled the wrong thing. This is why this is called variational Monte Carlo. I'm taking just Monte Carlo to compute expectation values for my variational state. And the other one is action-based Monte Carlo, which really is an unbiased estimator for your observable. So there's kind of a very clear distinction here. So what I have to show you now is my personal wish list, or our to-do list. We have to construct these psis. We have to efficiently calculate probabilities, because we have to do that a lot of times. It's a Monte Carlo algorithm after all. And we have to figure out whether these states are useful. And this is unfortunately the last thing that we're doing, because you only see it when you do numerics on them.
Say it once again, the
Yes.
capital G, script G acts on the vertices, and the DG acts on the edges, or was it the other way around?
And the capital G is just kind of a configuration of gauge fields. It's a very classical thing. It's just kind of a a configuration of, let's say, if you take a Z2 lattice gauge theory, it would be up or down.
Yeah.
So you have one configuration of up, down, up, down, up, down, up, down. And that just tells you that you get a certain probability for that one configuration. And you get a certain value for your observable for that configuration as well. Now you change one of the spins or many of the spins, you get another configuration, capital G, and you get another value there. And then you just start iterating. And hopefully with a bit of importance sampling, you go to the right expectation value. Does that kind of solve the question? So there's nothing acting here on anything with that big G, it's just sitting somewhere. And it's sitting on the links because it's a gauge field.
Okay, then please go back
Yes.
one slide. Yes, and one more slide. And one more slide.
Okay, sure, here we go.
So the psi, capital Psi, should live in
Yes.
your Hilbert space.
Yes, it does.
So it should be described both by states on the vertices and by states on the edges.
It does.
Somehow the states on the edge, the part that describes the states on the edges seems to have disappeared when you wrote capital Psi 2 slides further down.
Yes.
Because if you're doing inner product psi psi, so I expect the edge part
Yes.
to occur quadratically. and
Yes,
it doesn't look quadratic here.
it's just normalized.
What?
So it's normalized to 1. So all of them, it's also normal basis that I'm picking for the capital G's. So you have kind of two, well, D is missing, but you have two parts that are meeting there. They are a delta function. And so they are all canceling out if they're not equal. And if they're equal, they're normalized to 1. So they just fall away. So this is also the first hint, like the way we encode probabilities here is actually in the norm of the psi f's. So big note, these are not normalized states because this is what we use to encode probability in these settings. Okay, so constructing a state. Well, if you come from Ignacio's group, there's one way how you do states. No, just joking, of course, there are many ways how you can do states, but one of them is tensor networks. And so the whole idea of that project and the kind of the early works here are done by Ares mostly, is that local tensors can lead to local gauge symmetries. That's the whole idea. If you can pack something local on a lattice, you are hopefully able to encode local symmetries. And this is a whole idea of kind of building a tensor and a projector, just the way that we had it before. We have stuff living on the link, living on the sides, then projecting it together with these kind of turquoise bubbles. Now they become pink here, but they do the same job. So that's the idea of the thing that we're going to do. These are the kind of expression that we're using. Since there are fermions on the lattice, the idea is you can use fermions all the way through instead of mixing fermions and bosons in the middle, because that is going to be a real nightmare to kind of keep track of who's commuting with whom. So this is a whole fermionic tensor network. You'll also notice that there's kind of a bit of a special structure, and we're coming back to that in a minute. So the idea here is we take tensors, we take projectors, we put it all together, and hopefully we have an interesting state. So this is the first step. You have the vacuum of everything. So this is now the Fock basis, the Fock vacuum, no fermions anywhere. And you start putting things, you put tensors. This is a rather boring state. This is basically a product state, right? Nothing is, yeah.
Just from my understanding, so the big blobs are the fermions,
Yes.
the other ones are the gauge fields.
There are no gauge fields yet, so I'm kind of misleading you slightly here. I'm stringing you along a bit. So gauge fields will enter in a second. Right now, we're just building a fermionic state. So this is just the psi f. And then we'll put in the gauge fields later, because I thought it might be kind of more easy to grasp what we're kind of gluing together if we're doing one species at a time. So this is just fermions being glued together.
What is the vacuum state for computer scientists?
Ah, sorry.
There's nothing.
Yeah, that's a very good answer. If you have a fermion, it can be either occupied or non-occupied.
No, like, so you think of it as a string, like many
Like
qubits in zero
all-
state?
All bits 0, yes.
Okay.
It's just not bits because it's fermion, so you have to be careful that if you create something that minus signs, if you have to commute through. So it's a bit more of a kind of a nasty beast than just qubit 0. But for all kind of illustrative purposes, it's kind of zeros on all bits.
But you can put all the minus signs in the operation and annihilation operators, right? So you can just keep the computational basis states.
Sure. So, yeah, sure. There's something even cooler in our case. if you kind of start counting how many fermionic operators there are per A and per omega, it's always kind of divisible by 2. So I'm really sure that I will have no signs anywhere, because kind of quadratic operators in fermions will be like bosons, basically. They will kind of not create any minus signs anywhere. This is one of the beauty of that approach. The second beauty will be coming in a second. So yeah, here we go. Now we have our first part. Now this is kind of the first setting, like blue dots. And now we have to do something more to create a state. And this is putting projectors in the middle. Okay, so now we have a fermionic state, but it's not quite psi f of g yet. So this is not a mishap in typing there. This is actually globally invariant. So what's the difference between a global invariance and a local invariance? Global invariance is something like particle number conservation. You would kind of count the numbers of particles on your whole system, and you say it can't change globally. Here we have something more. Each vertex has actually a conservation law. So each vertex has to conserve the incoming and outgoing electric fields to make sure that it fits to the value of the number of fermions on that vertex. And this is not done by that thing because there are no gauge fields yet. So there's another step that we have to do. And usually this part of the talk takes like 15 minutes. And I shrunk it down to one single slide, which is I draw more legs. So there's kind of a bit of magic happening here. I'm going to give you an intuition. If you want to discuss that in great detail, I'm very happy to do that. It's kind of one of the beautiful parts of the paper that usually ends up in a single slide, which is you have to put in something that depends on the gauge fields down here. So something that depends on the configuration of the G's in order to make your fermionic state adhere to the local symmetries. And this construction here, and I hit all the ugliness under the rug, is in that U. What we're doing is we're making the fermions on the links, so these artificial, these virtual fermions that are living on the links, which are the same as your virtual degrees of freedom in the normal MPS, thinking black legs again. Like the black legs are being contracted out at the end, but we make them aware of the gauge field. And by doing that in a clever way, we are able to show that these states are actually locally gauge invariant. What does it mean? You're acting with the gauge transformation on one of the big blue legs, like the long ones of the fermions. You can show that the state doesn't change.
Sorry, like,
Yes.
what is a leg with a leg? I mean, is there?
Sorry, what? Sorry,
A
what?
leg with a leg, is there a small tensor sitting there? I mean, you have like a leg sticking out of.
Yes, this is a leg with a leg.
Yeah, what does that mean?
And that just means that it is a bit of abuse of notation here. So what that exactly means is that this fermion, like there's kind of these R's and like, let's give names to things. Up, right, left, down are 4 black lines. And this is the name that we're going to use for our virtual fermions. So the ones that are contracted out in the end, which is exactly what that that state here does, kind of gets rid of all the virtual degrees of freedom. So only the blue stuff remains. That's the whole idea. And now the idea of having that small blue line emanating out of the black line there just means that this fermion that's living on that link will be aware of the gauge field. So it will change depending on the gauge field. If you feel more comfortable, you could draw a small box there that it acts on. It's just kind of a bit of quick notation. If you draw these things on a piece of paper, at some point you stop drawing the kind of boxes and you just kind of make a line there.
But this is basically to later on chuck something on there, or not?
Yes.
So you just now add the leg so you can influence it later on.
Precisely. So your Hamiltonian will have h degrees of freedom that will be kind of putting operators from the top on these small blue legs, and that will influence the state on all levels. That's the idea.
Why are you projecting also on these omega phi? What is that like?
Yeah.
These small omega.
Yeah. So the capital omega here was the vacuum of everything, so all fermionic modes, which means the physical ones, the blue ones coming on top, and all the black ones which are living on the lattice building my state. Now, if you want to have a state that only lives on the physical fermions, you have to get rid of all the black stuff somehow. And this is just what that thing does. This is basically the big sum over all the contractions that you usually do in front of an MPS to make sure that all your matrices are contracted. These are just not matrices, they are fermionic operators with some weight. So you have to make sure that they vanish somehow. So basically tracing out, imagine the black lines being closed, you're tracing out the physical fermions. Sorry, the virtual fermions, the physical fermions stay, otherwise you don't have a state. Okay, so now we have a state. Now we have to figure out how we can compute with that thing, because that was item number 2. Item number 2 was being able to efficiently compute with that thing. And there was one cool thing about quadratic operators, it's no signs. There's another cool thing about quadratic operators. This will be a Gaussian state. So this will be a fermionic Gaussian state, which means you just put it in a covariance matrix and you're happy. Covariance matrix means that if I want the squared overlap, I just compute a determinant of a matrix and I'm done. Like there's no real PEPS algorithm behind here. Like there's no real contraction going on because PEPS contractions are really expensive. And we don't want to do that every time we run our Monte Carlo sample. What we want to do is we just want to have something cheap. And now we are in a highly restrictive class of states, right? So fermionic Gaussian states tend to produce together with a product state and then a big O superposition of those. Now the big question is, are these states actually useful? Because, well, I just showed you that we can construct them. I hope you believe me that they're kind of useful. And so now the only question is, can we do anything with that? And we take that Hamiltonian there, which is the Z2 version of the Hilbert-Susskind Hamiltonian, which is basically a very, very drastically simplified version of quantum electrodynamics. And we throw away all the fermions. Like I told you about fermions for the last, let's say, 30, 40 minutes. And now we're throwing them away. Why? Because it's a nice benchmarking example. You can get Monte Carlo data for these systems, so you have something that you can compare to. So this is what you get. And what you can see is like the variational Monte Carlo's VMC. You have the expectation value of the energy on the left side. You have your coupling parameter on the x-axis. And you have two versions of that state. One is called optimized and the other is minimal. That is basically just our convention for calling the bond dimension. Like bond dimension minimal is just a single fermion per link. And then you can put 2 fermions per link. And if you're fancy, you can put 3 or 4 fermions per link. And then you see that you're very close to ED. This is, of course, for a very small system. So 2 by 2. This is not very impressive because you can do ED on it. So what happens if you take a larger system? You can start kind of building it up and kind of do variational, like do real action-based quantum Monte Carlo on top of that. And you see that with just, I think 4 parameters is what we had here, you can very precisely fit that whole curve. And that's just our way of saying these states are useful. You can learn something with about the system with these states. And then there's obviously 2 other questions that you could be asking. Great, Patrick, you did 2D. Who's interested in 2D? And the next question is then what happens in 3 spatial dimensions. This is something that we have been recently working on, kind of figuring out how to make these tensor networks in 3 dimensions, actually still with a computationally efficiently ansatz, but making sure that all the rotation and symmetries are correct. And what happens if you add back the fermions? And this is something that Ariel should be giving a talk at some point about, because that's his PhD that he's currently doing. And I hope that the paper about that will be out very soon. So this was supposed to be much quicker than it actually was. So now there's 2 more things that I could talk about, but I think I shouldn't.
Yeah. So what is the computationally most demanding step in this? Is it computing the determinant?
No, actually not, because you can update the determinant. So if you do a local change on a matrix, you can update that determinant incrementally. The same goes for the inverse. So there's some inverses, but we can update them and the determinants. What actually the most expensive step is, and I never thought that it would be, is the gradient of the norm. Like if you want to get the gradients because you want to optimize your state, your parameters of the state in some direction, you have to compute the gradient of the norm. And that in our case is 4 matrices of full system size that we have to multiply. And we're now looking into putting that actually on GPUs, or kind of, for example, if you have the trace of 4 matrices, you can split it into 2 and not do the outer product act, like the real last product, but just take the diagonal entries directly. So we're trying to play tricks on how to make that faster. But that's actually the slowest step in that whole procedure. So if you just give me a state and I'm supposed to evaluate it, it's much quicker than if you give me a Hamiltonian, I'm supposed to minimize it.
Can you compare it to this quantum Monte Carlo? And how much time did that cost?
Like in that case, when you can run it, it basically runs on a laptop computer. Like that's considerably faster than what we are doing, but it won't work anymore as soon as you put the fermions. So there's kind of a trade-off. You're like, of course, like benchmarking against a well-known method, we are losing against that method right now. But then, of course, the question is, if you start kind of going to the directions where they are not very prone to excel, then this might be a way to kind of find a niche where that algorithm is kind of useful. Like also, like big picture, quantum Monte Carlo is a genius method. Like it's very good. Like action-based Monte Carlo is great. It's a thing that they compare with at CERN. Like if you see any theoretical predictions, that's what they're using. Like we don't expect to compete with them in computing that. The idea is just there are certain system configurations that you by definition or well, by convergence cannot do. So then we are hoping to give some additional data in these ranges, like developing from the 17th until now highly optimized code. There's very little hope that with kind of 5 years of research, you would be kind of beating that on their home turf. So now to question what you're interested in. Like, I'm happy to take that.
One more question.
Yeah, sure.
So in constructing these states, you make actually a lot more choices than just kind of the structure of the state, right? Like you choose that these fermionic operators are quadratic.
Yes.
Right?
Yeah.
Like you could also choose not to do this.
Yes, you could. But then these operators here would look very different.
Yes.
So then we would have just a more general choice. For example, you could imagine adding another term to that to that thing. It suddenly becomes a lot more difficult than to kind of build norms or build observables with these states, like actual numerical values. And so the whole idea here is if you keep it Gaussian, you kind of can use all these determinant tricks that I told you or hinted at. If you don't do that, it gets much more involved because you actually have to contract two fermionic pepsids together. And that scales exponentially.
Yeah, then I understand. Do you know kind of what you lose by making these choices? Like, is there a clear example that you suddenly cannot reach anymore because it's like Gaussian?
So we try to do the opposite to a certain degree. So we can prove that we can reach both limits of that theory, which is interesting because then you know that your state can, in theory, span kind of the whole valid range of that thing. It's hard to get an intuition of what we're losing. So I wouldn't expect these things to be great if you're going to excited states when really kind of dynamics kicks in. But that's just me kind of making a guess. So I can do 2 minutes on each, if that's interesting for you. Like just highlighting and opening it up for discussion a bit, like this is the idea. And then if anybody's interested in that, happy to discuss over lunch about that. Does that sound reasonable to you? Sure. Okay. So this is a project with Mengyao, Iloik, Tim, and Jordi. And it's a bit on the idea of tensor networks together with tropical algebra. Whom of you know what tropical algebra is? Okay, so then we are kind of doing the quick slide on tropical algebra. Like I'm skipping the entanglement introduction, like all of you work on quantum information, you most probably know much more about that than I do. So the idea here is if you take two numbers and you add them, you usually get the sum of the two. I'm free to define this algebra if I feel like it, or somebody else did so before me. The addition becomes the minimum and the multiplication becomes the addition. And this is all there is. The thing is actually kind of like French mathematicians have a weird way to honor people. That's all I'm saying here, because this is called tropical algebra because two Brazilian mathematicians became very prominent at this. And to honor them, they named it tropical. I personally would have chosen their last names, but you know. What you can do with these algebra or with this algebra is you can look at the adjacency matrix of a graph and you just put everything that's not connected to infinity and the weights on the and the rest. And you can ask questions about this. So as a kind of optimization tool, for example, for what is the shortest path in 2 steps? You just matrix multiply these together and then you can kind of convince yourself that in exactly 2 steps, these are the shortest path in the graph. Now, you can also ask what is the shortest in up to 2 steps. So either I do it directly, for example, going from 1 to 2 takes 2 instead of infinity because I can't go from 1 to 2 in 2 steps because there is no 2-step path to that graph. Now, me talking about that, I'm not a mathematician myself, so I wouldn't do this if there wasn't a reason in physics for this. The idea is if you want to have classical bounds for Bell inequalities, these actually become hard to compute at some point. So if you're not in that easy setting of a CHSH inequality where you can just enumerate all the settings, then you suddenly have to think about how do I get my classical bounds? So how do I what do I base my inequality on? And we are trying to use exactly that to reformulate the classical bound of an inequality as a tropical tensor network. Because now if you take more bodies up there, you can define the interactions between these two, like all the strategies, as tropical matrices, and then contracting the tensor network exactly gives you your tropical bound, like your classical bound that you're looking for. And that's kind of the 2 minutes on that project. If you want to kind of know why we are kind of interested in that and what kind of the pitfalls are, there's lunch for that. And all these slides
A
go.
tropical tensor network means that you're contracting the matrices according
Yes.
to the tensor.
Yeah, like instead of doing a sum over matrix multiplication, the idea is to take a minimum of the addition of all the terms, which is very natural if you're thinking about graphs. The minimum of the addition is kind of I'm going via any other node to the other node. And this would be here, like I'm going via any other strategy and kind of combine these two nodes together to one bigger one. And this is what we're trying to do here. So now, if we're tensor networks talking, you could think about what happens if I do different connections. You could think about, can we import more of that tropical algebra into kind of Bell inequality settings? So for example, what does the tropical eigenvalue suddenly mean? If you're thinking about Bell inequalities, what does the tropical eigenvector correspond to? So these things are something that we're doing together with Tim and Mengyao and Jordi, trying to kind of build a bit of a dictionary.
Is there a tropical singular line decomposition?
I'm not aware of it, but that maybe just means that I don't know it. That doesn't mean that it doesn't exist. It's kind of like tropical eigenvalues, for example, are a bit of a tricky beast. There's only one. And then this can have a degenerate eigenspace of eigenvectors, but you know that there's only a single eigenvalue for each matrix. So that's kind of a bit weird, and then I don't know how that translates to a singular value decomposition. I just don't know. Okay, and now my 2 cents on tensor networks and topological data analysis. That's a project with Alice, Casper, Jory, and Vedran. And the idea there is, if you're like, we're doing the same kind of quiz question, who knows what topological data analysis is? Okay, that's way more, so we can skip the first 3 slides. I'm just going to lose 1 sentence on that. It's basically, usually you have classification tasks you're interested in, is it a cat or is it a dog? Maybe there are more difficult computational tasks in classification, which mean that you don't look at kind of in a convolutional sense at local features, but you have to look at more global features. And one way of doing this is persistent homology, which means that you're kind of defining simplicial complexes on top of data points, and we're not going into any of the details here. The idea is that vanishing and appearing of features here can be used as a signature that you can classify on. That's all I'm saying. Happy to discuss that in greater length over lunch. Now, the idea here is there are certain numbers which are kind of, for example, classify the number of holes. And if Chris is listening, I'm sorry to butcher that part that badly. I'm happy to discuss with you a lot more on this. Like you have kind of 4 simplices here, and if you're talking about a click complex, everything that is a full click on a graph is filled. And if it's not but connected, then it can be a hole. In that case, this would be a 1-dimensional hole because there's kind of a connection around it, but it's not cross-filled, so it's not filled. A number of these holes can be used to classify as well, just not the appearance and disappearance, but also the total number of features at a given kind of, for a given simplicial complex. And now if we look at these Betti numbers, these become hard to compute if you're going to high K, so if you're going to high dimensional holes. There has been a very interesting mapping that has been explored recently in complexity proofs by Marcos Coxinho, who gave the first talk at QIP, for example, and Chris Cate. So that kind of talk about the cheese and the hole in the cheese. And I think it was a very beautiful talk. And he kind of explained that, how to use that for QMA1 hardness of I think, cohomology or homology problems. And now what we can do is you can map the object that characterizes these Betti numbers, like that you use to count Betti numbers, to a physical Hamiltonian. And that's suddenly when I'm back in the game, because this is a Hamiltonian that lives somewhere. Now I can suddenly think about, can I do tensor networks methods on that? And maybe count the number of ground states just by repeatedly minimizing the energy and asking myself whether this is another ground state. I know a lot of properties because these are supersymmetric Hamiltonians in physics, so maybe we can exploit that. And actually, Karl-Jan has done a lot of work on these kind of constrained systems. And so, yeah, that's something that I would love to discuss with you. And then finally, we can think about like, why could that be hard? Because, well, free lunch doesn't exist outside here usually. So if you're mapping kind of an arbitrary graph to a tensor network, you'll usually have a problem of finding a good order of that thing. Like, how do you actually properly put that thing on a line? Because my MPS numerics will be very different depending on how closeness is defined. Because long range entangled things are hard in MPS. And then the second thing is, of course, there's a lot of local symmetries going on here. And how do we enforce that properly? Do we design the tensors like we did in the first project? Or do we enforce it with an energy term? Like, all these things are still open. And I'm happy to discuss with you about all of this if you're interested. And with that, thank you for your attention.